Center at New Delhi. However, I was registered at Kurukshetra University, but I was, all experimental work like on the ion beam I did there. And at the outset, I would also like to thank all my teachers. Professor Naresh sir is there, Professor Mahavir sir, and all the organizing team, especially the principal, Professor Baljinder Singh ji. Thank you all. So let me start this. So after I think I worked in many organizations, and in 2009 I came to Punjab University as an assistant professor in physical sciences. So there I saw that there are a lot of scopes if you work in a multidisciplinary area. So being a physicist and you are there for solving the problems which are related with the, you can say, the forensic science or related with the, because I am heading now two laboratories. One is the lab which is doing synthesis for many materials, many smart materials. Yesterday we got a patent. So Dr. Shama is my student, and you saw how hydrogel can, make wonders for many applications. So since she was there, Dr. Vijay is again my collaborator from MIT. So I thought that I should go for something different, where I just want to let you know that physics or chemistry or the natural sciences could also be applied to the areas like forensic science. So I have two things to talk to you. Like we started this work like some work on the nanophosphors. So what nanophosphor can do, we know that they can make LED, they can make SCRT, flexible devices, all mobiles and all these things. So we thought why to utilize certain properties which are very remarkable at the nanoscale to apply it for finger mark sensing. For other sensors we are also working, but here I will be focusing on this. And another area which is, because being a student of say MSc Physics or Chemistry, you are using spectroscopic method and you are generating huge data. So now it's an era of data science, where you can say how machine learning, chemometrics, all these things, how they can be applied so that you can get some good information from that data, and from pattern recognition techniques you can find out whether this thing belongs to this category or this category. Even now people are working like from single blood sample you do Raman or IR and you can say whether this person is having cancerous growth or not. So that's just on the basis of data. So you are having, so there are certain methods where you can do pattern recognition. So one of my collaborators is working on this. So let me start with we started, however, we were working in a collaboration to make the nanophosphor for other application, but I saw this could be applied to the other area, so I will be discussing some applications here. So for the student point of view, just want to show that you know about luminescence, right? So you are supplying certain energy, and as an emission you are getting certain photons, say in the visible region. So this is nothing but excitation of photon is there, and then you can say that because non-radiative excitation is also there, relaxation is also there, because excited states are having very, very less lifetime of the order of 10 to minus 8 seconds. So all these electrons cannot reside on this, they have to go down, and then you have a conduction band, and again the release of energy in the form of luminescence. Now these luminescence are of many types. We call it as a photoluminescence, right? So you are applying here the excitation source is the light. You have a bioluminescence, so the biochemical reactions are there. You have a radioluminescence where you are applying gamma radiations or other kind of radiation. Cathodoluminescence where you are applying electron or in the electric field. Then you have a sonoluminescence, like you are exciting it with the sound. Then thermoluminescence, like you are exciting the material with the heat energy. Then triboluminescence means luminescence is created by rubbing a material and generating an energy due to friction, and then chemiluminescence. All the applications, they are available already in nature if we talk about these phenomena. So what is phosphor and what is nanophosphor? So any material where we are talking about, let me tell you this one also. So if we talk about the fluorescence, that is basically if you are applying energy, this energy, and immediately you are getting the luminescence, right? But phosphorescence, that is what I can say, it is delayed luminescence. Phosphorescence is a delayed reaction. So you can see this one will come maybe phosphorescence. So phosphorescence, that you are applying the energy, then switch off the energy, and again you are getting the luminescence. So we have prepared one phosphor. When you apply a photon energy for for few seconds, and then you switch off the photon, this UV lamp, it will excite up to 1 hour. So that is persistent long after glow phosphorus. So this could be applied like I thought it could be applied from for a trace evidence which are there in a crime area. So we have made a aerosol can, say you have a fingerprint over there, and the investigating agency do not know that where are the fingerprints. So you spray all over the room, switch off all the lights, and then switch UV light for once and switch off. So where the fingerprint would be there, so that will glow. So ultimately it will help. So that is a simple application if you talk about in that sense. So these are the materials. So we have a bulk phosphor. Now we thought that why to reduce its size to various applications, to various methods, so that we could get some more desired properties. Like that at nanoscale, less than 100 nanometer, the surface area increases. So surface to volume ratio is very, very high. That is the reason that the quantum effects comes into picture, and that will change all the properties other than the bulk phosphor. So bulk phosphor having this property, but the nanophosphor will be having a very, very extremely different property. They are being used for wide LED, CRT. All these things are now there in dosimetry also for measurement of the dose when you enter into the radiation area. They have very large advantages. You can coat it, you can make it the lamp or a display panel. For example, you can say in plasma display, these are the materials which are being used. Zinc sulfide is used widely. Then these are the YAG cerium-3, yttrium aluminum garnite. These are the crystals which you can make. I'll tell you how we tell you the synthesis method also. Another example which I saw, this was in Nature Materials, and you say that this in vivo activation of persistent nanophosphor for optical imaging of vascularization and tumors and grafted cells. So these are being used to find out the tumors. So that is again another application of these nanophosphors. So in detail you can read this article. This is just similarly about the LEDs. These are being widely used. How they are being used? They are from the nanophosphor only. And these materials are having very high CRI, that is color rendering index. So sun is having CRI of the 100. Say, so CRI is basically that if you have a light source, and then how effectively it will distinguish the different color of that object. So that is CRI. And LEDs or these nanophosphor are having CRI of the 75. So that is, it means these materials could also be used in those applications. So we thought that because these materials exhibit different properties and we have certain problems in finger mark sensing. Like investigating agency are still using micro level powders, which sometimes cannot give result up to the mark of that level, so that they could identify a person. But that is a bigger challenge as on date also. So we started working 6-7 years back, and so I'll skip these. We are using here alkali and alkali oxides also, and these are basically the reason that because of they can accommodate large variety of impurities because band gap is very large. Good optical physical properties. They are easy to synthesize. They are chemically stable also, and maybe they require less expensive. So I will be discussing about all these materials which we have synthesized and their application also. So ultimately, I told you the problems that how we can go for this. So that answer will come at the end of the application part. But here the micro level powder, because you see you have these secretions. You see these ridges are there on your fingers. You see how much width is there for one ridge? Have you thought? They are unique patterns. They are going to be used for personal identification also. But you see that they are of the micrometer order size. So agencies are using micrometer level powder. So if you are filling the ridges with a micrometer particle powder, so ultimately it will pose a greater problem as far as the contrast or as far as the identification is there. So that is our motivation. So these are the material which, and then I'll tell you about, we have characterized this material. So one method is a very simple method like solid state route, and we make it like you have certain precursor material, you mix it, and then you place it in a muffled furnace for 6 hours of the order of say 900 or plus or 800 degree, and then you will see certain powder, and then you can grind or you can bar mill, and then you can do that. But sometimes we have seen that because this 800 temperature is very less, so complete diffusion is not there of the dopant, or sometimes you see that the pure phase is, sometimes you will not get the pure phase. It's a mixed phase. So mixed phase means the output desired luminescence will not be there, right? So that is the problem. So we went for the another route that is called combustion. So what we thought that we take metal nitrates. Say I am going to make, on the next slide I will show you an example. So you take some metal nitrate, as a fuel I take a urea, and then but oxidizer to fuel ratio should be 1, and then I'll balance this equation. I make it a uniform paste, and then heat it up of the order of 550 degrees centigrade. Now this method we are not going up to 800, so it means up to 550 we can start the reaction. But when the ignition starts and this explosion kind of thing happen in this reaction, so it will create a temperature more than 3000 degrees. So that is the beauty, that all the material is converted at this temperature. All material converts into nanomaterial. So this is the beauty, that you have kept the temperature low, but fuel is there which is playing the role. And then you can see if most of the powders they converted into a pure phase, but if you see that some of the peaks are not safe, we will go for the XRD. I will show you to see whether a pure phase is there or mixed phase is there. So from XRD we can find out the particle size as well as rough estimation, that is device error, give you rough estimation. I hope all the basic things you know already, like particle size, XRD, or should I go more basic into? Any response from backside, students? Yes? You know about like how to characterize the material using X-ray diffraction. XRD means X-ray diffraction because it's with flow. Sometimes we use the shorter terms. So maybe, so if you have any query, you can raise your hand, right? So then, so the detailed reaction I'll show you. So you have a precursor, like you want to make a calcium aluminate europium dispersive dope, right? So we have a two dopants. So ultimately you have to keep calcium nitrate, aluminium nitrate, and then the fuel, right? And the dopant you can take as you desire. You have to take the oxidized to fuel as a one. Then you have to homogenize this mixture, rigorous stirring, then heating at 500. Even we have also initiated this reaction at 450 also. Maybe this can be initiated. So again, low temperature. So then solution concentrate, they undergo self-ignition, and then this white foam formation will be there. And you will see in the, I'll show you in the temp picture that you will see very large voids in the, the prepared samples. That is due to when the blast happens. So this combustion reaction happens, so all the gases will escape. So that will create the voids. Ultimately, you grind it, and then you will see, you will get this nanophosphor. So this phosphor you can also make in your laboratory. That is why I have showed you. It's a very simple reaction. So in that sense, you can go and change the dopant and then get the desired luminescence or whatever wavelength you want. So one can do for the dilatation work on the master level, and then do for some kind of application. So these are we will see the characterization part, and then the PL and the thermoluminescence. Okay. So what we do when we synthesize the material, so we'll check whether the material is in that phase which we have prepared for that. Say that is, so the basic technique is X-ray diffraction, where you can say that ultimately for a crystalline material you for X-ray, and then the diffracted X-rays from the various atoms are recorded by the detector, right? And you can say that if you are changing the angle, so it means you are recording say theta, because we do not start from 0 degree, ultimately the incident X-ray will interfere. So we will start say from 10 degree or 15 degree or 5 degree, and then go up to say 65 or 70. Again, we will not go beyond 90 degree, because ultimately backscattered X-ray will come into picture, so that is not our purpose. We just want to scan the X-ray diffracted from this prepared powder only. So this is how we do. So that is why on the x-axis you always have a 2 theta, and on y-axis you have an intensity. So you will see that one is the prepared powder, this is the upper one, and lower one is the powder which is from the standard JCPDS card. So they are all the instruments are having a library, so they will match all the phases, and they will tell that whether all the phases are matched or not. So sometimes we say some mixed phase are always there, so we go for say annealing, or maybe we go for at say we will keep the sample at higher degree for say 4 hours, so that the mixed phase also converts into that pure phase. So this is how we do. So more clear picture for strontium aluminate, europium dispersive doped nanophosphor, and you can say upper one is the prepared powder, the lower one is the JCPDS standard. Similarly, the XRD, and then you can say the scanning electron microscope for this strontium aluminate. Again, the temp picture. So I saw you that the X-ray peaks. So from these X-ray peaks also, from Debye-Scherrer formula, we can calculate the particle size, but that is a rough estimation. So XRD will not give you an exact result. That is why we go for the TAMP, transmission electron microscope. So that will confirm whether the particle size in that range or not. So you can see the bar is of 100 nanometer. So all the particle ranges from 20 to 30 nanometers. Similarly for others, you can see the composition, they are varying. SrAl2O4, SrAl12, O90. So phase is different for all the materials. Similarly for 41425. Then another characterization method, we go for EDX, energy dispersive X-rays. basically what is happening, like in field emission scanning electron microscope, we have an attachment, extra attachment for X-ray detection also. And you know that when the X-rays are coming out of the material, so they are giving you certain information about the elemental profile of that material. That is why you see that these are the like peaks for dispersium. So these are the, you can see on x-axis energy is there, kilo electron volt. So X-ray energy is there. So from these spectra you can find out whether any impurity is there or not. So because you are doing this reaction, so maybe your chemical is impure or some other kind of impurity. Like we do this reaction in a crucible or in a even a borosilicate. So borosilicate, we have seen that it can go up to 900 or maybe not beyond 1000, but we do this reaction in a simple borosilicate glass. So whether any impurity from the other glass or some kind of, so from here you can see no other peak other than material, like you have a calcium, aluminium, you have certain oxygen peaks, you can see all these are the X-ray, and on y-axis you have counts per second, like this is the intensity. So similarly, for optical property we do photoluminescence for those materials, right? So you will excite the material with a certain wavelength. Excitation will excite all the electrons to the excited state. Then non-radiative transitions, they come to the metastable state, and then again they will come down and they will give you a luminescence peak, and they are in the visual region. Now to know about that the emission is at what wavelength emission is there, so we'll do these PL measurements, and you see for this phosphor you have multiple wavelengths. 614 is the major, but you see a 590, right? 654, 703. So one thing is this that for our application desired wavelength is 614. So we'll apply filter for other wavelength and let this 614 go out, right? Or there are other methods like I'll tell you later on, like ion beam irradiation also. So we can tailor this wavelength. So we can see that with how much flux we can tailor and how much flux with we can do this desired. Now you see from PL we can find out, this is the CIE chromaticity diagram. This one. So CIE chromaticity diagram will tell you about the emission wavelength as well as the color of that phosphor. So say the people are working on white LEDs, they want that this point, which for this phosphor it is on the red side, but they want that it should come like it should come here. So this is perfect white LED. So that is why those people who are working on LED, they tailor those materials so that this comes here. So this is again another beautiful application, how to tailor those materials so that you can get the desired wavelength. So like you see, here we have added various dopants. So Ca-Al2O4, europium 3+. So only one dopant is there. So you see for blue 614, maximum intensity is for blue. So it means 1.5 mole percent is only giving you the highest intensity. So it means europium is fixed now, that is at 1.5%. Now you go for adding the dispersium, the another one. So and another thing, concentration quenching is another effect I'll show you. You see after 1.5%, 2%, 4%, the intensity is decreasing. So this effect is called concentration quenching. You see that these are increasing up to 1.5 and then coming down after 1.5, right? So this, it means that the desired optimized concentration of europium is only 1.5%. Beyond that वो कहीं side पे नहीं जाएगा. It will not go to those defect sites. वो ऐसे ही पड़ा रहेगा. So it is showing that the optimum concentration. So all these things we have to optimize before the desired applications. Screen is white. Fourteen 25, and all these things I am skipping these. Which transitions are responsible to give you certain wavelengths? So they are emission wavelengths. So from energy level diagram one can know about this. So in this chromaticity diagram you see that like you see these are the x and y coordinate for this material. So they are showing that this it is almost, you can see that the blue and you can see the blue and yellow is mixture of blue and yellow will give you this color for this luminescence. So then for another material, aluminum oxide europium dope, you will see the XRD, PL, and then the particle size. So you can see from every particle size it is 11 nanometer. So you see that. So again another factor that when you reduce the particle size, again the properties of that material again change, right? So if, like I said, that in a bulk material behaves different, in a nano it behaves different. So for similarly for other material, now we'll do some applications in the finger mark sensing. So this material we have already prepared, material is ready, they are in the nanoform. Now see that how it can sense the finger mark. But before the finger mark sensing, in few slides I'll tell you about fingerprint है क्या और investigating agency क्या करती है इसके साथ. I'll tell you certain background. You know that whenever we touch something, some object, fingerprint is deposited. You know that why it is there? Because they have a secretion glands. So we always secrete, and ultimately transfer of secretions is there from particular person to the object, and this fingerprint will tell that I was there, right? I was there at some time. So it will show you the connection between my fingerprint, myself, and the crime scene, right? And they do not change. ये भी एक जनरल आपको बेसिक्स बता रहा हूँ, ये कभी चेंज नहीं होते, राइट? सो इट मीन ये हमारी पर्सनल आइडेंटिटी जो है वो रिवील कर रहे हैं. एंड इन यूआईडी कार्ड वी हैव ऑलरेडी गिवन द डाटाबेस, राइट? हमने सभी ने बनाया आधार कार्ड, so already fingerprint is there with the you can say the agency or the government, right? So they have certain character, they have general character, so that we can identify later on. So you see, like I tell you a brief history. So like this, the Galton identify इनके कोई pattern है, इनको कुछ हम बोलते हैं. Don't go into the detail, just आपको बता रहा हूँ. इसके बाद हमने application कैसे कर ली. So they are double loop, arc है, dent है. You will see that all these things are already here. And in 1858, that was some work did by this chief magistrate, that William Herschel. He was in India during time, and for your information, first fingerprint bureau of the world was in India, in Kolkata. First fingerprint bureau of the world. So it means a lot of work was there at that time in India. And even this slide shows that how we can inspire from our observations. Like this, you see Henry Ford. So he published the paper in the Nature Journal in 1880, and the paper was, he was fond of making a pottery, and he saw on his pots that certain prints are there, because before that nobody knows कि fingerprint भी होते हैं. So he systematically worked on these and then published in the Nature. So this is how we can inspire from nature or from our observation, what we are doing. और कुछ nature में हो रहा है उसमें sometimes we inspire. So this is an example that he published, the first work on this. And I told you that why we deposit, because of we have a epidermis, we have a dermis and dermal papillae. So all these connected with the glands, and you deposit these. So I'll go into the application part. And what are the composition of these secretions? You know about mechanisms of water, and then organic part, and then inorganic part. So you know about this. So they are being deposited on the object. So investigating agency know about these details. Now I'll show you that till date the people are using the powder which sometimes do not reveal certain information which maybe could lead to the benefit of doubt that further. But if you are using these nanophosphor, they will give you all the details. So these are the Manisha points normally जो इन्वेस्टिगेटिंग एजेंसी मैच करती है फिंगरप्रिंट में, या आपके मोबाइल में लैपटॉप में फिंगरप्रिंट मैचिंग का फंक्शन है ना, वो भी यही कर रहा है. एक एल्गोरिदम एक प्रोग्राम है, उसमें वो पैटर्न देख रहा है सबसे पहले, देन इट विल ड्रॉ इट्स Manisha डिटेल्स, राइट, एंड देन इट विल से दैट this percent of match is there, then it will pass, otherwise it will reject. This simple program is there. So this is, but you see, whenever crime happen or at that place, the criminal is not sometimes they do not touch that object in that way that it could deposit a good print. So that is the problem, that ultimately you are not able to get complete information from those kind of objects for real samples. Now if somebody says, or I will say that deposits of your fingerprint, आप बड़े अच्छे से लगाओगे, but criminal अच्छे से तो लगाएगा नहीं, तो वो chance print, right? So that is why this information is required. So all these Manisha details are there, so I will not go into it, just letting you people that what matching is being done later on, and even for your mobile also, the fingerprint sensor, they work on this principle. So this is a fingerprint from crime scene, and this is from, say, the ink print. So this is, you see, information are there, so they will match, like bifurcation is there, same bifurcation is there, so then regending is there, regending is there, bifurcation is there, so eyelet, all these points are already there, so they are just matching, but the location is very, very important. So those regending will be on the same location of that finger mark. Okay. So you have certain method, like if you know about, you have people from chemistry, they know about, you can go for iodine fuming, but the problem is iodine evaporate. You can go for cyanoacrylate, but again cyanoacrylate is a carcinogenic, so a lot of problems already there. We can go for those methods. We have certain ninhydrin, another chemical, silver nitrate deposition, another chemical, but lot of problems are there. So this is I will show you. This is a fingerprint I deposited on a mobile screen. So you see that in the normal light you cannot say that on this part fingerprint is there. So this is again problem which people face while searching the crime scene. This is the micro level powder, but again you are not able to find out the reach detail and all these things. So that will give benefit of doubt for those people who are involved in the crime. So the similar scenario is there. Okay, so we thought why to, then we applied, now you see, maybe due to intensity, are you able to see this? So you see that this is nanophosphor finger mark and fingerprint, and you see that all the points and the details are already revealed. So you have written and being included, delta, code, bifurcation, all these things are there. So it means ultimately, and why it happens, because the particle size are in the nano range, so ultimately you filled the ranges of the order of micrometer with the nano, so it means ultimately you get the contrast. And this is having a strong luminescence, so that will give you an extra edge. And also if your surface is black, say, so you can go for white nanophosphor. If you have, so you can generate the contrast. So you can tailor this material to get the desired color, desired wavelength. So that is again a beauty. But in agencies they are having white or black. Only two things are there. So this thing, and you will see various prints on different surfaces. On laptop it is looking good, but I don't know, maybe intensity thing is there. So you can see, yeah. Thank you, sir. Then we did certain tests, like you deposited the prints, say 30 prints, single nanophosphor, and you say that up to what number it is being sensed. So that is depletion series. So we see that it is working, say up to 25 or more than 25. Then you see you have some objects where the normal powder does not work. जो बैकग्राउंड है इसमें वो इंटरफेयर करती है, जैसे न्यूज़पेपर के ऊपर प्रिंट हो तो नॉर्मल पाउडर, ब्लैक पाउडर, व्हाइट पाउडर काम नहीं करेगा, तो बैकग्राउंड इतना ज़्यादा इंटरफेयर करेगा, राइट. यू हैव कोक कैन, तो बार उस पर बार वो होता है ना. So similarly, this is being done with this. So because they are having, they will show you long after glow, means UV को डाला, ऑफ कर दिया, अभी भी ग्लो कर रहा है, अब बैकग्राउंड ग्लो नहीं कर रही है, right? So I'll show you, like we deposited it in on a currency node. So currency node, if you apply these powders and you apply UV, तो वो ग्लो ही करता रहेगा, नोड भी ग्लो करेगा, पाउडर भी ग्लो करेगा. So currency node luminescence will interfere this. So that is a gain problem. So that we solved with this. You see ये in pictures में, इन तीनों picture में you see UV is there, but इसमें हमने ऑफ कर दिया. So this problem is being जो बार की वजह से आ रही थी वो रिमूव हो गई, right? So then again on mouse also, computer optical mouse, normal powder does not work. This is being published in General Material Science. Again, you see on the credit card. On the currency note, you see this is again normal powder. You see the interference is there, and then you see the when UV is switched off, the currency is not glowing. So this is long after glow, 1 घंटे तक ग्लो करता रहेगा. हमने ऑफ कर दिया, करेंसी ग्लो नहीं कर रहा है, एक्साइटेशन है नहीं है, तो आपको वो एक्सपर्ट जो है अपना उस टाइम तक सारा काम कर सकता है. सो दिस वाज अ जेन्युइन प्रॉब्लम व्हिच वी आर एबल टू सॉल्व दिस ऑन अ CD, you can say. Then on aluminium foil, all these objects which we took, normally we got it in the crime scene. Then all the different particles on different surfaces. This is SRAL204, europium dispersium, and this is on the glass slide. So you see how beautifully we are able to remove these problems, right? So initially you saw this, that we have these like you want to find out the delta, you want to find out the core, delta, core, all these things it can be revealed. So this is one application which we resolved, and maybe for the lip mark also, because they are also unique. Lip mark also we did this work, and then we found that they could it works. So say lip mark on the glass. So they are there already, crime is there, but they sometimes they are not able to, because maybe cosmetics or other products will hinder, right? So quickly I'll tell you the other applications. So this is how we have tailored with the fifth heavy ions, we have changed the wavelength and all these things, so they are so quickly I'll maybe sir we have 5 or 10 minutes, 5 minutes, 2 minutes, okay. So quickly I'll tell you the another application with the just changing the slide also. So we saw various evidences, and then we utilize the IR as well as Raman, and then certain machine learning methods and chemometrics. Because normally we do spectroscopy, we do lot of data generation is there, but ultimately what inference we could find out from the data, so that we did from here. So I'll show you certain slides. I'll show you certain slides like my published work. So these are the basics for IR and Raman. This you know. We have applied these mathematical models. So these are the, like you know about AI, artificial intelligence. So AI, artificial intelligence, indirectly we have applied in forensic science. So there are certain methods of machine learning which can work on a big data. So you have a, say, 1,000 number of samples are scanned with a Raman, and you have this data. Now Raman is working from, say, or IR, say 400 to 4,000 centimeter inverse. So कितना wave number का range है? And for one particular wave number you have one variable. So that will go up to say 3,600 variable. So कोई statistical method you know that which can handle 3,600 variables. So that is the major challenge. So we utilize the machine learning method to handle all the variables and then get an information from the sample, whether query is there, whether the evidence which belongs to this place is also connected with this person or not. This could be any other kind of thing. So I'll tell you मैंने क्या क्या प्रॉब्लम सॉल्व करी, ये सारे मेथड लगा के, उसमें हम आर प्रोग्रामिंग भी कर रहे हैं, मैटलैब भी कर रहे हैं, बिकॉज ये चीजें अब आगे आने वाले टाइम का फ्यूचर है. आपके पास डाटा है, चाहे वो स्पेक्ट्रोस्कोपिक है, XRD है, किसी भी तरीके का. you want to see certain pattern, you want to see certain results. So this is just, I'm skipping this. We find out the likelihood ratio also. I'll tell you this was published, can we identify that a lipstick stain in the crime scene or on the glass could be linked to a person. So this already we published recently. Again, the certain crimes which happen to the child. So you have a kohol. So could we link those things with, then you have the crime where sunscreen is being transferred from one person to another. So can we link that? So all these problems we already solved. Then I'll tell you certain more interesting application. I'll skip this. Creams. You have lot of products, whether it is original or a fake. You can find out with these methods, but you have to generate the data for the standard. So you have a standard library, and then you apply the model and then check with your sample. So this could be done. Even food forensics, environment forensics, all these things. So even we have find out, you have a cigarette ash. So from ash we find out what was the brand. So this how we work. So this is again with the Raman and IR, simple, and then machine learning. Then wood trafficking is another big challenge. So we are working on this, and we have recently published that this species belongs to which place. So we are working on the geographical locations of the species using again the spectroscopic method. So this is again a beautiful application, hardwood, softwood identification. We already did this. Then this soil belongs to this place or that place. Salman Khan Black Buck case. Soil was being transferred from that place to another. The soil is an evidence. Again, the spectroscopic method, all spectroscopic and chemometric. And now we are moving on to machine learning also. This fingernail clipping is from male or a female. Another problem. So this was published in Microchemical. So beautifully we explained. Then another application I'll show you. Yeah. You see SAM and TEM photograph, EDS is also there. So whether this printout was taken from this printer or not. This is again, you have a document, you see, right? So one page is being changed. That is a will or that is any kind of legal document. So वो change हुआ, वो print तो किया, लेकिन वो toner composition जो है, बाकी pages की same है, लेकिन second number page की different है. So from the toner composition, we solved this problem. It's already published. again with the Raman, this is again for the, so whether it is from inkjet or a laser or a photocopy, इतना भी बता दे रहा हूँ कि किससे किया है। वेरी बहुत छोटी छोटी चीजें, लेकिन जब हम सोचते हैं कि ये भी प्रॉब्लम हो सकती है, लाइक कोर्ट में बहुत सारी क्वेरीज होती हैं कि ये जो हैंड राइटिंग है ये लिखी कब गई थी, क्वेरी है। लाइक वी गॉट कॉल फ्रॉम ए डीसी कुल्लू लास्ट ईयर, और क्वेरी क्या थी कि देयर वाज लैंड वाज अलॉटेड बाय द राजा ऑफ कुल्लू एट दैट टाइम, तो उन्होंने वो हाथ से लिख के दे दिया भी ये तुम्हारी मतलब है ना। अब उसको वहां पे होटल बन गए, बड़ा कुछ बन गया, तो गवर्नमेंट ने कहा कि ये लोगों को रजिस्टर्ड कर देते, रजिस्ट्रियां कर देते। उन्होंने न्यूज़पेपर में निकाला कि जिसके पास है राजा के डॉक्यूमेंट है वो लेके आ जाए, है ना। तो जितनी जमीन नहीं थी उससे ज्यादा डॉक्यूमेंट आ गए। सब ये ऑथेंटिकेट करना है, ये उसी टाइम का लिखा गया था या कब का था ना। दिस इज अगेन ए बिग चैलेंज एंड द प्रॉपर्टी बिलोंग्स टू करोड़ ऑफ रुपीज। सो वी CFSL FSL जुंगा पीपल केम टू अस, उन्होंने 2-4 दिन हमने लगा के उस प्रॉब्लम को सॉल्व किया। सो अल्टीमेटली बिकॉज फेक एंड ऑल दीज थिंग्स, like last month I visited USA for one conference, and when I appeared for a visa at US Embassy, so she asked, you just explain what your talk all about. So she was handling my passport and I started with passport. Passport के fraud words कितने हैं, मैं उसी के लिए solution देने जा रहा हूँ। So that was certain kind of things which even people are facing. Like the Dharamshala lab is getting most of these passport fraud cases. Foreigners overstayed and फिर वो किसी तरीके से बनाते हैं और वो सारे करते हैं. So all these things even a physicist or a chemist can work. I tell you, right? और सिंपल मेथड्स हैं जो आपकी बेसिक्स स्पेक्ट्रोस्कोपी है और बाकी चीजें आपने यूज करनी है। सो इट डिपेंड्स उसकी कंपोजिशन, उससे आपको इंस्पिरेशन लेनी है कि इस कंपोजिशन को कैसे रिवील कर सकते हैं। सो पेपर, एक पेपर की एज कितनी है, दिस इज ऑलरेडी डन, ऑल दीज थिंग्स एंड फ्यूचर इज लाइक AI एंड ऑल दीज थिंग्स। So you must know about machine learning क्या है, AI क्या है, and if you want to read something more about, so this is recently published by Royal Society of Chemistry. So with me, my collaborators are there from Australia, and thank you very much. Thank you.